All right, so we can go ahead and get this rolling. So at the end of Tuesday, we were looking at the moderation question. And basically what we found is that there is a moderating effect of birth region such that the effect of discrimination or those discrimination perceptions differs depending on whether you were US born or foreign born. And so then this last part of our homework is hierarchical logistic regression. And in this case, what we're wanting to say is, okay, well, what if we wanted to add in socioeconomic status information? Trying to find my spot here. One thing on the moderation stuff, just real quick, if you were wanting to then decompose this interaction, basically all you would do is you would separate and you would do two separate models, one for US born and one for foreign born. And so that would look something like this. Where all you're doing is you're just subsetting the data frame. So it's the exact same model copied and pasted, only we added this indexing brackets to say like this model, mod int US versus mod int 4. And this one we're saying the data is the data frame, but specifically the data frame where birth region n equals 0, and running that model. And then for this one, it's that same thing except for where birth region equals 1. Run those models, and then you can do those ANOVAs and look at those log odds, all that sort of stuff for each of the separate subsamples to break down that interaction and see what those different moderating effects are. And I believe you should. Yeah, and you can, if you're on that live code, you can just copy and paste that big chunk of code over into your script. I'm going to go ahead and move on to number 26 here. And for this one, we're going to do slightly different models. So we're going to focus on depression, self-esteem, and sex, but then also a second model where we add in socioeconomic status, mother and father's education. So for the first bit, you have to check the linearity of the logit. And who remembers how you check that linearity of the logit? Not everybody at once. This is the one that's kind of inconvenient and kind of a pain.
You do the GLM and then you pull the log of
right.
the
For each of those continuous variables, you're going to include an interaction with the continuous variable and the product with the log of itself. So in this case, one other thing is that this popped up after I set the data set, so there are some missing values that we need to get rid of for mother ed, father ed, and SES. So we'll start by taking our data frame, piping it into a filter, and filtering out where mother ed.f, father ed.f, or SES.n are NA. And then we'll start with the regular part of the model where we have dep2.n predicted by dep1, se1, sex.n, ses.n, motherEd.in, fatherEd.in. As far as I put F up here and N down here, we need to use the N's in the model. You could change these to N because anything that's missing .F will be missing .N. I don't know why I put the .F in the filter, but it doesn't matter anyway, it's arbitrary. And then we need to add in all of these interactions. So we'll have the I dep1 times the log of dep1 plus I se1 times the log of se1 plus ses So once we get all of those interactions with their logs put in, we add in that, we're still using that binomial, we're using Logistic here, and then just pipe that straight into summary. Since we don't need to save this model, this is just at a glance. And again, for this one, we're looking at each of these interactions down here, and we hope for, and what we find is that none of these are significant, so we can say, yep, our assumption of linearity of logit is in good standing.
And that is the linear relationship between the ID and the logit transformed values?
That once you apply that logit link, there is a linear relationship there, yeah.
If you were to find that there was not linearity of the logit, what steps might you take to kind of resolve that issue?
That's going to vary a lot on a case-by-case basis. It may be a matter of needing to transform the variable by some means. It may just be that you need to remove that particular variable and that it would be inappropriate to try to include that variable. But basically, the same kind of principles would apply for anything else that's violating an assumption. Is starting with okay, well, is there some way that we can transform this variable that then meets these assumptions? Would be kind of your step one. From there, I would say you just Google violating linearity of logit and look for answers that fit with your particular case of, well, mine is violating it in this way. Is there some sort of transformation or some sort of approach that would be a robust thing? Because that could be another thing, is that it may be that there's some robust standard error estimator that can be put in, but that really depends on the specific situation of your analysis, and so I can't really give you a better answer than that outside of to say that it would be possible, but ultimately it could end up being something that you just can't use that particular variable the way you were hoping to. All right, so then
Symmetrical linearity, we use the VIF tolerance, right?
yep.
And then I noticed that there's a car version and a desk tools version.
And I use the car version, although presumably they give you the exact same thing. I'm not sure what one versus the other would give you. The only reason we use desk tools, or we even load desk tools, is for the pseudo R squared function, whereas we use PSYC for a lot of stuff, and especially with the next unit when we get into PCA, it's like most of what we do is from that PSYC library, and so I just use what I'm familiar with. So now we're going to create two separate models using these variables. Like I said, in the first one, we want just dep1, se1, and sexn, and then that's going to be our compact model. And then for the augmented model, we also want to add in SES, mother ed, and father ed. So first, let's create that compact model. And once again, we'll have to start by filtering out some variables.
So this is number 27?
Yes. I mean, technically we're still on 26 because we got to check the multiclinearity, but to do that we have to make our models. So once we filter out those missing things, then we just create our model. That first model is just dep1.c, se1.c, and sex.n. My naming conventions, mod.c. Why is that? Mod.c means that compact model. And then for the augmented model, we do the same thing, but now we're adding in those 3 additional variables.
What are we doing with these filtering out?
Because in the data, at the very beginning, we had that like filtering out unit 3 filter where I'd gone through and I'd already like annotated whether keep or remove it was remove if they were missing one of the variables that we had been using. But I had already created that data set before I got to this last problem. Went, oh shit, there's 3 other variables that I forgot to include in this filter. Although, you could argue that, it's probably better to do it this way, because if you also filtered out the people who were missing all these for the first analyses, then you're just unnecessarily taking people out. So there are missing values for these variables, and so now that we're using those variables, we have to take out those NAs or else it's not going to work.
Okay. For the compact model, do we need to do that?
I mean, that's a good point. I guess technically, no, you don't, since we're not actually putting them in those models. So you could just leave that out. That was, I started from the augmented model, then worked back to the compact and just copied and pasted. And so that's how it went.
That's what I was confused.
So now that we've got our 2 models made, we can check for multiclinearity with that VIF package. So we look at the VIF function of our mod C, and then 1 divided by VIF of mod C, and then same thing for mod A. Run those. And if you need a reminder, I'm pretty sure I put it in the script up the first time we talked about this. Right here. That tolerance should be greater than 0.1 and VIF should be less than 10. So when we look at our VIFs here, 1.2, 1 to 1.03. This tolerance down here, 0.78, 0.8, 0.96. And then for the augmented model, same thing. When we're looking at our VIF, they're all clearly lower than 10, so we're good there. And then that tolerance, everything is above 0.1, so we're good there as well. All right, so then when we get to number 27, this is where somebody was asking on Tuesday about why it says step 1 in the previous things. And what we were talking about is that this is that hierarchical because we're doing it in multiple steps and we're just adding in additional information and seeing how does that affect our models. So step one would be that compact model. So when you do your analysis for that compact model, what does it look like? And then step two is when you add in those additional variables with that augmented model. And so if we look at our all the same tables as before, if I could spell. And so our this would be step one, where we're looking at that compact model. As far as reporting that chi-square, p-value, and Nagle-Kirke's pseudo-R squared, where are we getting that information? How are we going to report that information for this step one here?
You have to subtract the null and residuals.
Yep, so the deviance here, or the difference between deviance of the null and residual models, will be the chi-square statistic. The difference in degrees of freedom will be the degrees of freedom for that chi-square test. And then you can use the p chi-square function to put those two things in. So it would be, we've got 3 degrees of freedom, so chi-square in parentheses 3 equals 175.98, and p is substantially less than 0.001. And that would be what you would report for step one. For step two, you're reporting all the same stuff, except you're changing the .c to .a to switch to that augmented model. And now we have 6 degrees of freedom. So chi-square in parentheses 6 equals 186.43. And then once again, p is less than 0.001. And then as far as running those R squared, same things as before. Spelling is hard. N-A-G-L-Q-E-R-K. Oh. There we go. So we have our pseudo R squared for each of those. And the final thing that you'd want to do with these models, now that we have those, you know, that's kind of like that omnibus test of each model. But now the question is that augmented model significantly better than the compact model? So once we add in socioeconomic status, mother and father's education, does that actually improve the model itself? So now instead of comparing this within each model, comparing the full model to a null model, here we want to compare one full model to the other full model. So who can take a guess at how you would make that comparison? That's one way you could do it, yeah. Putting them both in ANOVA, the LM support package, the model compare function as well. But more abstractly, all we're doing now is instead of comparing the null deviance to the residual deviance, we're wanting to compare that residual deviance between the two separate models. So this would really just be a matter of so now our degrees of freedom will be the difference in degrees of freedom in the compact model and the augmented model. Your chi-square statistic is going to be the difference in that deviance between the compact and augmented model. And then plug those things into the p chi-square, and we can see our p is 0.002. And so, yes, this augmented model does significantly improve beyond adding these 3 additional variables does significantly improve our model. And then for those who were in the GLM course, you'll recognize, as we just mentioned, the LM support model compare function, where you just put in your compact and augmented models, and it will also do a model comparison. Although this is conceptually the same, it's a little bit different because it's looking for sum of squared errors, which is not what we're dealing with in the logistic world. Or same thing, putting when you put 2 models into ANOVA, you can get kind of that same test of comparing those differences, and if it's significant, then yes, there is a significant improvement in the model.
Is there an alternative package of LM support won't install for us? Or just doing the
You could. Okay, so AOV doesn't work. What about ANOVA? There we go. Nope, not that. That's a good question, because the other one doesn't actually work with GLM models. But, I mean, you can just look at those deviances and check it out that way. It's really unfortunate if LM support won't install, because as far as doing linear models, it is a phenomenal and incredibly useful library. And so then that's the end of the homework. What does this tell you about the incremental value of these variables? That adding these variables in, it does significantly improve our model. What I was going to do now with the rest of this time, I had talked about a little bit about the predict functions and doing some stuff with graphing. And so all I'm going to do is copy and paste over some code, and we'll kind of walk through this and talk about what's going on. So you should be able to copy and paste this, over from that live code. Or does anybody have any questions about the homework before we kind of talk about graphing?
Is there going to be an example write-up, I guess, in the book?
Yeah, I was about to say, I'm pretty sure there's one in the book. So for this, we're gonna go back to the MRAS data set, which I briefly skimmed earlier, and it's women's labor force participation. LFP is labor force participation, either yes or no. It's our dichotomous variable. That'll be our dependent variable. This HC variable is husband college, whether or not the husband in the household went to college or not. LWG is log wages, I believe. Log expected wage rate, so we'll be messing with that a little bit. And income, exclusive of the wife's income, will be the variables that we're playing with today. This data comes from the car package, and so you can just call it explicitly if you haven't loaded the car library by saying car data. So load that in. We're gonna make that labor force participation a 0 and 1 variable, where 1 is yes and 0 is no. For the husband in college, yes will be coded as 0.5 and no will be coded as negative 0.5. And then we're going to make this model where we're predicting labor force participation by the log wages and whether or not the husband is in college. And so then I'm going to create my convention whenever I'm making specific data frames that are just for plots is just to call it, plot DF. And in this case, we're going to use expand grid. I'm going to tell it LWG is a sequence from the minimum value of LWG to the maximum value of LWG by increments of 0.1. And I'm setting HCC 1 to 0, although that should be, yeah.
What does expand grid do again?
Well, that's what I was about to say. So if we look here now at what the results of what that does is it takes everything that you put into it and it crosses it. So if, for instance, we said this equals A, B, and C, and we run that. Now if we look at plot DF2, it takes this sequence that we gave it and crosses it, so it gives all of those values for A, all of those values for B, and all of those values for C. If you put free things in there, it outputs every possible combination of anything that you put into it. So if you're trying to do more than one thing, instead of creating a data frame, you just use expand grid, so it'll automatically cross all the stuff for you and output a data frame of all the different combinations. But in this case, by setting HCC 1 to 0, is that big enough? By setting that to 0, we're actually collapsing across husband college at this point because it's all coded as 0.5 and negative 0.5. So by predicting for 0, we're predicting they're in between those two groups and just averaging across them. So we have our plot data frame. And now to break this part down, because I have several things going on here with the C-bind and binding the actual plot data frame onto these predictions. But first, let's look at these predictions. So if we just run this subset or subsection of the data here with the predict GLM, and we're saying to predict based on this mod X that we created. For the new data, use plot DF2, which is here, where all we did was we took that log wage rate and then have that sequence of 0.1. So across all of these different things, plug each of those into those coefficients for log wages. And then for HCC1, just plug in 0 for everything and give us some prediction. Because we have type equals response, it's going to give us the probability. And then se.fit equals true is what gives us the confidence intervals. So if we just run that predict, not the whole line, it will give us our predictions here. So for that first observation, the prediction is 0.144. For the next one, it's 0.152, et cetera, et cetera. So then all I'm doing now is I'm saying, okay, take that and bind it together with the original data frame so that we have an LWG column, an HCC1 column, plus now this the fit and the confidence interval columns. And so now when we look at plot DF2, we have just that. So we have our original columns, but then plus here we have our fit, which is the actual probability for that specific observation, and then the SE fit. I think I just ran that twice. There we go. And so, like I said, we now have that SE fit. And so now using this data frame, we will start making our plot. So here, just starting by making the actual base plot, I like theme classic. And then, so for this first thing, I'm just gonna run up to here where we're running this geom jitter. And so all this is doing is it's saying that for X, we want our X to be that LWG. Our Y, we want labor force participation, yes or no. The height and width here is just how much it lets the points jitter. Because for instance, if instead of using geom jitter, if we just used geom point, and then take out this height and width thing, here's what it would look like. So that jitter just says, all right, throw in some random movement in around these things. And the height tells you how much you're gonna let it jitter top to bottom, and then the width will be how much it jitters from side to side. So if we, oops. If we change that, and say we make the height, 0.3 and run it, it's going to give us a, much wider thing there. So it really just depends on the specific plot and the data. You have to kind of play around with it, and it until you find something that looks, nice, I suppose. And then you just make sure to indicate, like in your figure notes, that points are jittered to avoid overlapping data points or whatever. Like make sure that they know that this might not be the exact value of that person's LWG. It might be over here, or it might be over here. It just depends. But so now that we have that base plot, we add in, and that's coming from the data itself. That's that raw data. But now we want to add in our regression line based on plot DF2, which is what we just created right here. So if we go ahead and run that next line and tell it add geom line, where the data equals that plot data frame that we created, X equals LWG and Y equals fit, it now gives us that, that's our actual, prediction line. Then for the next two lines, we're telling it, same thing, we want other lines, only this time, Y, we're doing 1.96 times that SE fit. If we go back and look at the data frame that it created, because we have that SE fit equals true, it's giving us that standard error. To convert standard error to confidence intervals, you multiply it by 1.96. So we're saying for this line, take the prediction and add 0.05573, or add whatever that 1.96 times the standard error, and then make that a dashed line, and then do the same thing but subtract it to make another dashed line. And so now we have our confidence intervals around our lines. The reason I'm using this data set instead of our data set that we've been using is because the graphs are particularly uninteresting because it's a huge data set, tiny standard errors, like it's not really clear. So one thing to keep in mind, but so this is how you could do this across one variable. But say we wanted to break things down other ways as well. So here I have an if-else statement where we're looking at the income and basically doing a median split on the income. So I'm taking DF2 income, and if it's greater than the median of DF2 income, label it high. If it's not, label it as low. And we're going to call that income dike here. And then we have, we're going to create a new model using LWG, and this time income. Getting plus and minus 1 standard deviation of income, concatenating those as I don't know why this is being slow today. So now we have two values, 8.49 and 31.76, which is the mean minus and plus 1 standard deviation. Doing the same thing that we did before as far as getting our thing. Now here, remember earlier we set that one value as 0, so you could have just used data frame instead of expand grid. But here, I'm saying give me that same sequence from the minimum to the maximum by 0.1 of LWG, and then for inc equals inc, but inc is now 2 values. So when you run this now, this is just being so slow today. So now it's going to give us that LWG for where inc is minus 1 standard deviation across all of these values, and then here's where it's plus 1 standard deviation, which is what that expand grid is going to give us.
What does the by argument do?
That tells it like if you just say a sequence from 1 to 4, it's going to output 1, 2, 3, 4. But if you say by 0.5, then it's going to say 1, 1.5, 2, 2.5. So it's telling it what to increase by in the sequence. Yeah.
Gotcha. Oh, okay, we're predicting a fit line.
Right.
Gotcha.
And so we need some sort of sequence. And then here we're doing the same thing that we did before, only now we're using our plot mod, this new model that we've created, and this new data frame that we've created. The predict GLM will give us that the fit and the SE and whatnot, and then cbind will bind that with the data frame that we created here. So after we take a look at that, we now have all of our predictions for here is that minus 1 standard deviation plus the fit, which will be our regression line, and that standard error. And then here we have all of that plus 1 standard deviation. Here I'm just creating a dichotomous income variable in the plot data frame. which I think I use for coloring purposes, which we'll find out here soon. Because now here we're going to do the same thing. When we run our geom jitter, so color is where we got that dichotomous, or the reason I created this dichotomous variable in that plot data frame. So same thing as before, only now I'm also including to color it based on that dichotomous income factor that we just created. Then for the lines, there's one subtle difference. If you leave out a grouping variable, here's what, if we try to fit this regression line. There. In this case, because we already have it broken down by color, this is learning something new, that actually groups it for us because it has to give it separate things for the color. If we didn't have that in there, if you ever see something that looks like this, so that's what the fit line looks like if you don't have some sort of grouping variable, and that's because for each point of LWG, it gives us two separate predictions, one for plus and one for minus. And so if you include group equals ink, then now it would correctly group those two separate things. So it realizes like, oh wait, these are two separate lines depending on this variable, not one line that zigzags back and forth between the two. Although what I learned today is that when you put in color and color those lines separately, you actually don't need to put in the group because no, stop, god damn it. The color automatically groups it together. And so in this case, we can see like here is that you can look at your probabilities broken down by high and low.
Can you do it where it's like a group of a different variable and color another variable?
Yeah, if you wanted to color it by, say, gender, like, in this case, it's all women, but yeah, like, I mean, it works just like anything else. Like, you could color it, you can change your point shapes, the sizes, the whatever. And that's the real beauty of ggplot is that, you can really do whatever you want to do.
Do you get the layman's interpretation of what this graph is saying?
So I would interpret this graph as, really, it depends on what your conceptual question of interest is, but for instance, you might want to see, like, at what point does it become a 50-50 shot that a woman is going to participate or not? And in this case, you could go across and say, like, all right, well, if they're in that lower, if they're below the median, like, down here at this point is where, like, you've got a 50% probability, but you have to come across, if you're in the high income group, this one, you're over here at, 2 of whatever. Probably not the best data to like try to make good things, but so you could imagine if instead, I almost pulled out the Titanic data set where it's just predicting survival or not of the Titanic, and you could think of it as, the lines for men and women, where you can say, like, all right, for women, like, their probability depending on their age is here, but like for men, it would be, there would definitely be an interaction there, where for men, like, the probability of not surviving is much higher regardless of age. And so just looking for those differential effects depending on what the variables are that you're breaking it down by. I'd have to look at this. Yeah, and so especially with the variable that we're plotting being the log wage rate, like that just really, like, part of the reason that we plot the probabilities just to get away from trying to think about logs, because I personally can't intuitively think about it at all. But if instead, like let's say that this was self-esteem down here on the x-axis, and foreign born and versus U.S. born, and what you can see is that for foreign born having low self-esteem doesn't necessarily predict that depression at time 2, but being U.S. born like already starts you out up here, but then maybe being foreign born, like once that self-esteem gets up higher, maybe they're really sensitive to criticism or whatever, blah blah blah.
So it's basically like the probability of whatever is on
Yeah,
the
so
line
as you
associated.
follow along this line, like that gives you that point estimate for what's the probability, that absolute probability, remembering that, when you're talking about the odds ratios, you're talking about that relative risk. This is the absolute risk in that probability space. And again, the only way that you can plot the raw data along with your models is by talking in terms of probability. The only other, this other one that I put up here, it's the exact same thing except for, filling in those bands instead of like using dotted lines. So it just kind of depends on what you're doing. It can be nice, like especially if say you're printing a poster for something and you need to print a black and white poster. Like being able to like shade in your confidence intervals bands can be helpful. I've done things before where like the actual lines were dashed, but like for one model it was filled in gray and the other was solid lines but with empty, so that you can still make those clear distinctions. And then from there it's really just a matter of making it pretty. So if I wanted to, one thing that I really like to do is, like this is really inefficient to have all this white space over here just because the legend is put over there. So if we just shift that legend over onto the plot itself, we can use that whole space for the plot, and you would do that by adjusting your theme and plot legend. Or is it legend position? Man, this is acting real fucky today. So legend position, there are some shortcuts that you can put as far as like, putting the word top and right and left and blah, blah, blah. Or if you just enter in 2 values. So if I put in legend position and then concatenate 0.5, 0.5, what that's going to do is it's going to move the legend to halfway across and halfway up. So from here you can just play with it to figure out where you want it to go. So let's say we go to like 0.8, 0.5. Let's make that 0.9, bump it over a little bit more, and then maybe it needs to come down a little bit. And there we go. So now instead of having just a shit ton of white space over here, I just shifted that legend over to make it a little bit more clear.
Could you change the background of the legend to be like?
Yeah, you can literally customize anything about this, and that'll all be in this theme. So like if I may need to look it up, but let's say legend background element. Oh, that's why it's acting fucky, because it's the live code and it keeps saving the script and interrupting what I'm trying to do. Element rectangle, color equals red, maybe. Oh, because there's a plus there and it doesn't need to be there. So that, element rectangle, color equals red, fill equals blue. Is that gonna? All right. Not something I necessarily deal with, but whenever you're working in the theme, if you just Google how to change my legend background, you'll be able to find, somebody's like, oh, well, it's, blah, blah, blah. Another thing that I really like to do is, like say you wanted to change these colors because you're not a big fan of seafoam green and salmon pink. I personally prefer using the manual adjustments. So in this case, we have our color, and I'll say we'll add on a scale color manual. And the reason I like using the manual is because first, it allows you to easily change. I don't want it to be ink dyke as my legend over there. And so I could make this say whatever I want to, because whatever you put in here is going to become the legend or the title of that legend. And then you'll say your values equal, and let's say we want instead red and blue. And now we want to change, because I don't like lowercase on my legend, so I want to change those too. I can also add here labels equals high and low. And it's going to change those labels as well. Now, the nice thing about using this manual method is that oftentimes we have several different things that are all overlapping. So maybe we also want the shapes by, let's go up here, and in our jitter we're going to add, instead of just having color, we're also going to add shapes equals ink dyke. So now we have circles for high and triangles for low, but notice how it gives us two separate legends even though it's the same variable. But when you use these manual things, let's scale shape manual. And then if the title that you put in is the same and the labels that you put in is the same, then it will combine those two separate plots. Only in this case, for our values, instead of red and blue, we can look at our ggplot shapes thing here, and zoom in on this thing. So these are all different shapes. So like 16 is a filled in circle, 17 is this triangle. It's kind of hard to see on the screen, but these are all black and these are filled with red. These are the fillable shapes. So there's actually two different arguments. Color will change this to blue or whatever. On these 21 through 25, color is the outline. So if you wanted, a red circle with a blue dot, this would be color equals red, fill equals blue. These are the filled shapes. But in this case, like say we wanted it to be, just 16 and 17, the circle and the triangle. So for our values, we just tell it 16 and 17. But now, because we have the same title and the same labels, it recognizes that, oh wait, we need to combine these two things. So now there's the red circle is high, the blue triangle is low, and it doesn't have one legend for the color and another legend for the shapes. So this is one of the main reasons that I really like to use the manual scales, whether it's color, shape, line type, any of those things that you can differentially using that manual prioritization of the legend can make your life a lot easier on the back end.
No way to easily manually adjust the axis numbers.
Yeah, that's a good point. So because there is no thing, let's say our y variable is a continuous variable. So we're going to scale y continuous. Now the biggest things will be your limits will be kind of like the minimum and maximum. Breaks is where you want your things. So let's say if we do breaks equals we'll say 0, 0.25, 0.5, 0.75, and 1. So now it's changed that to be like where each of those lines are. And these are your major breaks. There are also minor breaks. Where that could be important is like, say you wanted to add like the actual lines in for various things, or you might put if you just want a single line, like say you wanted a line at 0.5 just to see like where does that 50% go across this thing, then you would just add in a geom line and say that your y-intercept equals 0.5, and it'll put that line in for you. If instead you do want, say I like to do like a light gray dotted line for my major line so that it's there, but it's not like in your face, and it doesn't get too busy. And that would be another theme modification, that within the theme it's grid panel is it major? Oh wait, panel Y major? Nope. Major Y, there we go. And then only 1 equals, and so now it's gonna add those dotted lines, and so I could come up here and then also tell it like, I don't want it to be fucking black, so color equals gray. Make it a little bit more subtle back there, and you could go on from there to adjust more of those things. But then there's also like there's minor Y's. So in between all of these major breaks that I specified, there's actually minor grid lines. And so sometimes what you'll see is like the major ones may be numbered, but it'll also have like ticks that aren't numbered, and like those unnumbered ticks would be like your minor ticks, stuff like that. Same thing applies for if you're wanting to, for whatever reason, have lines across your X for your things, that it would just be panel grid major X, and changing that sort of stuff. What else? Titles and labels and stuff. Just adding labs, and title equals something. X equals log wages, Y equals labor force participation. And now notice here how like in between force and participation I don't have a space, and I just included this slash and n. That's a new line. So the way that it interprets that is, I need to break that down. So if we take that out and run it, then it's going to put it all in one line. But by including that in there, it breaks that participation down onto new line. And then, but of course, our titles or should be centered, going back to the theme. So come here to the theme, and we'll say plot title equals, and this will be an element text, and then h just equals 0.5. So telling it, like for our plot title, for the text of it, we want the horizontal justification to be 0.5, which is in the middle. It'll be, 0 if you want it left justified, 1 if you want it right justified, 0.5 for having it right in the middle. Same thing if you're looking to have it like ready for publication, so you need your titles, or like you need your graph to be in Times New Roman font. You can change your font here in the theme, all that good sort of stuff.
Do a facet grid.
Yeah, you could. If you wanted to say take this now and then facet it by let's say by, what was it, HCC1? Oops. And so now we have just have that same thing broken down, although if you're wanting to do it this way, you would have to also have that HCC1 in your plot DF that you predict on, because you'll have two separate regression things here for, depending on whether or not the husband has a college degree or not. So in this case, these aren't actually accurate, 'cause it's just replicating that same model that averages across the two. But if you were wanting to do that, you could just include that HCC1 in up here, up in here. And so then when you use your predict, it would also predict based on that HCC and give you two separate sets of, or I guess 4 separate sets of regression lines and confidence intervals. One thing as far as faceting that I'll point out is changing these labels is possible, but it's a huge pain. Like I have a specific script that I go back to and pull because I have like some helper functions and stuff and a weird way of going about it, such that if it's possible, instead of using this, like you would, if you wanted to facet it by this, just create a new factor where like code HCC1 as, no college degree and use that variable so that that's the labels that it automatically puts in there. Because adjusting the actual text inside those facet boxes can be a pretty huge pain. So much so I helped Anna create a plot for her for a meta-analysis that she was doing, and it was kind of like nested type stuff where along the side of the y-axis, like there were 3 big chunks of boxes, and then underneath those there would be like 3 smaller labels. Trying to get those to line up and have the right labels and stuff was such a pain that ultimately I decided, fuck it. I created a data frame that had a bunch of coordinates in it and just plotted actual like white boxes onto the plot, and then plotted like the labels that I wanted as text, and then just manually adjusted them to center them in the boxes and all that sort of stuff. So sometimes using these facets can be a pain as things get more complicated, but it's not too bad if you're just looking at quick and dirty things. Anything else?
Any different considerations for having a continuous y variable?
What's that?
If we have a continuous y variable, should do anything differently here?
Well, this is a continuous y variable actually, technically speaking. And especially when it comes to like my emphasis in data visualization is one of the main reasons that I adopted the habit of always having a factorized and a numeric version of everything. Because when it comes to visualization, those numeric variables are infinitely easier to work with than a categorical variable. Say we were looking at something and we're just looking across 4 groups and wanting to do any sort of plot of these 4 groups. Like you could just put that factor on your x-axis and it'll correctly, put all 4 of those. It'll label it for you, all that nice pretty stuff. But then say you want to put in like, a mean and confidence interval for each group. And so you want to put in, a dot with error bars, but you don't want that to be directly on top of your, bar or in the middle of all your jittered dots. So you need to offset it. If it's numeric and say those groups are coded as 1, 2, 3, and 4, it's really easy just to say like, all right, for this mean and error bar, like do x plus 0.5, and it will now shift that dot, and instead of putting it at 1 on top of everything else, it'll put it at 1.5. You can't do that as easily with factors. You have to use what's called position dodge stuff, and that stuff's always finicky, and I have to sit there and tinker with it to get it to play nice. But so when you're using those continuous variables, you can still make it look like factors, but it's just a lot easier to work with. And so that's why I prefer using the numeric versions of everything, especially for visualizations. The only time that can be kind of a hindrance is if you're trying to color and it's a new continuous variable. Even if it's only 2 values, it will try to do a scale thing. Which is fine in the sense that like the default scale is like blue to black, I think. And it'll still just give you, because everything is either 0 or 1, there's no in between, so everything will be blue or black. But in that case, all you have to do is wrap those continuous things. If it's a 4 group thing and labeled 1, 2, 3, 4, if you just wrap it in as factor, like inside ggplot, it will categorize it and have 4 discrete colors instead of that continuous gradient. But that's the kind of thing that you got to be mindful of when you're using continuous variables, but it's an easy fix. You just wrap it in as factor, and now you've got 4 discrete groups instead of this continuous fade. Anything else?
It's gonna save me like a lot of time. Okay, done this before.
If y'all ever have questions about like visualization and stuff, hit me up, let me know. Because if nothing else, I can tell you like, oh yeah, that'd be really easy, or like, it's possible, but like that's gonna take some. It's gonna take some tinkering and kind of messing with it. I've run into cases where, I have had to do some kind of roundabout ways to get some certain stuff done. But ultimately, like that's the beauty of ggplot, is that like if you can imagine it, you can plot it. It is just completely customizable in every possible way, and it really works. You can make some real pretty graphs with it, that's for sure. That and data visualization is a very in-demand skill these days. A lot of businesses are looking for people who are good with data analysis and data visualization, because that's the only way. Like executives don't understand stats, they understand pictures. Like if you can show them, then they're like, oh, okay, I see what's happening here. But if you're like, well, the slope of this is, it's like, they don't get it. But they do get pretty pictures. Anything else?
Homework's due on Thursday.
Yep. Don't see that.
I had an error with my Nagel-Kirky pseudo
Did you use type or which?
which object dot is not found.
That's
Where's that
sitting
sitting
here.
Well, my short and quick answer would be that I've mentioned before that sometimes some functions don't like to play nice with tidyverse stuff and with that like piping kind of thing. So worst case scenario, apply those filters and save it as a separate data frame, and then just put that data frame explicitly into your model instead of using the period. Because sometimes like that's one of the downsides of R, is that you know, with there being different versions of this, that, and the other, and like a lot of things depend on which version of, even if it's like we're all on the same version of desk tools, if it relies on some other package that you have a different version than I have, you know, that could cause problems, although I've now decided that in the future it should be that, like at the very beginning of the semester, the whole class gets on the same version of everything. Like all updates are installed and ready to go, so everybody's on the same versions and packages.
Jake found a package
Mhm.
that worked really well for me, because I wasn't able to load that up.
The desk tools thing, yeah.
It's working on number 9 though. It asks us the